Hi, good morning. Are there any questions? All right. Last time we proved this theorem. That's the last thing that we did. We wrote a proof for this. Now we know that A implies B is equivalent to negation of A or B, meaning this is an absolute theorem. So we can use it now. Now you combine the axiom of introduction of implication with this new result. Remember, the axiom told us that A implies B is equivalent to A or B equivalent to B. Now we also know that this is equivalent to negation of A or B. So using a Leibniz one step, we could prove this absolute theorem. You can substitute A implies B with negation of A is equivalent to B using Leibniz. And now the similar one is when you just shuffle these, because we have the symmetry of this junction. It's the same thing. So these are corollaries that we can get from our previous result. So I leave the details of the proof as exercise. Another corollary of this is that you can distribute implication over by implication. So A implies B is equivalent to C is equivalent to A implies B is equivalent to B, A implies C. All right, this is the distributivity of implication over by implication, which I leave the proof as exercise for you. You can try to do this one. Here, it's convenient to use the following notation for our next theorem, that instead of writing negation of A is equivalent to B, so we understand this as A is not equivalent to B, right? We've used the notation that is more convenient, and we use this symbol. And note that this symbol is not really officially part of the alphabet. It's just a notation that we use for the convenience, right? So when you see A is not equivalent to B like this, what you should understand is that this is in fact this string of symbols, is this formula. So just to make the notation simpler, as you can see, if you wanted to write this theorem, you're going to need a lot of negation. It gets confusing, but this way it's a lot easier to state the fact that these two are in fact equivalent, meaning A is not equivalent to B, and that is not equivalent to C is same as, or is equivalent to, A is not equivalent to B is not equivalent to C. Now, how do we prove this? In the proof, you should go back and put all the negations in their place. Let's start with the with this direction, and we're going to write an equational style and end with, I believe, this side. So what is this? This is the fact that negation, I mean, this formula here, what is it? It's a negation of A is not equivalent to B is equivalent to C. Now, A is not equivalent to B is the negation of A is equivalent to B. So on the left-hand side, we have this. Now use the axiom of of the introduction of negation. So just give me a second. Yeah, here, note that I didn't put the brackets here. So what we wanted to do is just take this formula as, let's call it formula D. negation of D is equivalent to D is equivalent to bottom, right? That's the axiom of introduction of negation. All right, now what do we do next? I mean, let's read this. I mean, it's going to take a few seconds to realize what to do, but I want you to practice reading the proofs using the annotations. Here it tells me that use this axiom, which is again introduction of bottom, right, applied to this formula. The negation of D is equivalent to D is equivalent to bottom. But now the C part is P is equivalent to C equivalent to bottom. That suggests me this has been taken to be P. And now this is replaced with something equivalent to it. But here it says this is equivalent to it. So you can replace negation of A is equivalent to B with A is equivalent to B equivalent to bottom. And this is exactly what is done here. We replace negation of A is equivalent to B with this formula here, which is equivalent to it. Now the next step, we have the axiom of symmetry of equivalence, negation of, sorry, the bottom is equivalent to C is equivalent to C is equivalent to bottom. And we're going to take this as our P and replace it with bottom is equivalent to C. No, sorry, not that one, this one. Here, again, if I didn't have an notation here, I would have been confused. But here it says that this part here is P. That means P is this. That means this is the part of the formula that we're substituting. And we're substituting it with C is equivalent to bottom. And now this is what we get. A is equivalent to B is equivalent to C is equivalent to bottom is equivalent to bottom. And the next step, again, read the annotations. What does it say? It says this formula here, B is equivalent to C equivalent to bottom, is same as negation of B is equivalent to bottom. So if I take P to be this formula in the middle, that is the C part is equivalent to P is equivalent to bottom, then I can replace B is equivalent to C equivalent to bottom with negation of B is equivalent to C. And this is what we get. Now, finally, what were we going to show? We're going to show this, which is the negation of A is equivalent to negation of B is equivalent to C. But this formula, if you again call it D, D is equivalent to bottom is equivalent to negation of D. Right? That's the axiom of introduction of negation. So it's the negation of D. You don't need Leibniz because I applied this for the entire formula. D is equivalent to bottom is equivalent to the negation of D. Any questions? See, this proof may have not been completely easy. Some of the steps are not trivial. Usually what you get in the exam or something is they're not going to be this difficult. But even when they're difficult, I mean, they're not, after some practice, they're not going to be as difficult. But also, you see the purpose of annotations here. The annotations help us to understand even difficult proofs. Yes? distribution of negation. Where is this? Yes, I mean this is just a shortcut or abbreviation for negation of A is equivalent to, now here is also negation of B is equivalent to C. Negation of B is equivalent to C. So we have this in mind and we know what we're going to, yes. No, I mean you don't have to. I mean, as I said, these are the same. I mean, this is really literally the same as this. It's just visually different, right? We consider these two to be the same formula. Now, last time we also proved that De Morgan. No, we didn't prove that De Morgan. So this is now we want to prove De Morgan. And this is a familiar one. You've all seen this before, that A and B as a proposition is equivalent to negation of A or negation of B. Might have seen it like this before, that negation of A and B is equivalent to negation of A or negation of B, but it's the same thing using double negation, right? Apply negation to both sides, you get the same thing. So this is just our De Morgan, but how do we prove this? Let's start with this side, which is more complicated. Negation of A or negation of B. Now negation of this formula, let's call this formula D, is equivalent to D is equivalent to bottom using the axiom of introduction of negation. So this is D equivalent to bottom. Now here you're going to, this step is a little bit tricky. What are we going to use? We are going to use this. Let me go back. This corollary here. That we know negation of A or B is equivalent to A or B equivalent to B. Now you apply that. Let me write that again here. So we know that we have proved that negation of A or B is equivalent to negation, well, sorry, A or B equivalent to B. Now this is true for any formulas A and B. Now I apply it for the case that B is negation of B instead of B. So everywhere you have negation of B. Right? Now we have this here. Let's call it P. The C part of the Leibniz is going to be P is equivalent to bottom. And this is the identity or equivalence that we are using. So we can replace P, this part, with this over here, because they're equivalent. So using Leibniz, we can replace or substitute this with this. Now again, the rest is going to be obvious because anytime you see negation of a formula is equivalent to bottom, you know it's equivalent to negation of that formula. So this is sorry, it's equivalent to the formula itself. So negation of B equivalent to bottom is equivalent to B. That's the axiom of introduction of negation. So you're going to take this to be P. The C part of the Leibniz is A or negation of B is equivalent to P. And now you're allowed to replace negation of B equivalent to bottom with B. Now apply the same theorem, but the one that was just the mirror image of the other of that one. We know that A or negation of B is equivalent to A or B equivalent to A, right? This is, let me show you, this is this one. So I can replace this with A or B equivalent to A. Using a Leibniz, I call this P. The C part of the Leibniz is P is equivalent to B, where P is always fresh. And you do this. Now, A or B equivalent to A equivalent to B gives us A and B. One of the axioms. Which axiom is that? Anyone remembers? All right, you need the list of axioms in front of you. Yeah, it's the golden rule. It's the one that says A and B is equivalent to A or B is equivalent to A is equivalent to B. So this is what we have. It's equivalent to this. And again, you don't need Leibniz because we are replacing the entire formula with something equivalent to it. Any questions? So a lot of proofs are similar. I'll do some of them. I'll leave some of them for you as an exercise. And now De Morgan, the second De Morgan, which is sort of a symmetric one, tells us that A or B is equivalent to negation of A or negation of A and negation of B. And you have seen again this in this form more likely, but it's the same. The proof is exercise. Actually, in order to prove this one, you don't have to go through the similar steps as this one. You can actually use this one. Now that you have the De Morgan for and, you can use it here for or. I'll leave the details as exercise. Here's a remark. The axiom of symmetry of by implication states that A is equivalent to B is equivalent to B equivalent to A. So you could move or shuffle the formulas around when you have consecutive by implication symbols, right? A is equivalent to B equivalent to C. Axiom of symmetry applied multiple times, it allows us to move things around. For example, if I have A is equivalent to C is equivalent to D equivalent to B, if I apply the axiom of symmetry enough times, then this would be equivalent to, so I'll just write if and only if in a equational style proof, to, for example, C is equivalent to B, B is equivalent to D is equivalent to A. They're the same, right? It's just the number of times that you need to apply this. Maybe 3 times apply the symmetry, and then you get this. Maybe twice. I don't exactly know. Probably 3 times is enough. But these are obvious things and obvious steps that in the future we might skip in the proof because just the very clear that we are using axiom of symmetry. Just like associativity that we said that we're not going to write because it's just clear that whenever you have statements like this, doesn't matter where the brackets are. So we could place the brackets anywhere we want without writing another step, because it's obvious that we are using associativity. In order to shorten our proofs, we do the same thing with the symmetry, and we do the same, and we are not going to write the step. One more thing that you have noticed, that axiom of symmetry, equation style proofs do not use equanimity, and that's just in the nature. It comes from the nature of how you write equation style, and that's actually one of the reasons that the equational style proofs sometimes have advantage over Hilbert style proof, because you could skip the, basically the equanimity step is embedded inside the equational style, so we don't use equanimity there. Let's have another theorem. Prove that A is equivalent to A and A. How do we do this? Let's see. Right. Let's start with the entire formula. Now I want to use the axiom of golden rule. Again, let me remind you what it says. It says A and B is equivalent to A, or B is equivalent to A is equivalent to B. Right? Now apply this for when B is also A. So another instance would be this. Now, as I said, with using the symmetry a few times, this would be the same as A and A is equivalent to, let's move things around, A is equivalent to A, or A is equivalent to A. So here I have this is equivalent to A, or A is equivalent to A. Now the last formula is an axiom. Right? It's idempotency of disjunction of OR. So our proof is done because this here is equivalent to an axiom. Therefore, it's an absolute theorem, right? By equanimity step. We just don't write equanimity because there's no need for it. Something that is equivalent to an absolute theorem must be an absolute theorem. The step you want to write a Hilbert style proof for that is going to just be application of one equanimity, which we skip. Two exercises. Show that A and B is equivalent to B and A. That means conjunction is also symmetric. Now, how do you prove this? I think one way to do this could be that you apply De Morgan, right? And instead of A and B, you know, A and B is equivalent to, sorry, I said A and B is equivalent to negation of A or negation of B by De Morgan, right? So if you wanted to write a Hilbert style proof, you just write it like this. And now you have the symmetry of OR. Apply it here, because that's an axiom. You get negation of B or negation of A. And now use the De Morgan again and convert it back to B and A. So, oh, that's clear. And also, conjunction is associative, meaning A and B and C is equivalent to A and B and C. Again, to prove this, since we have the associativity for disjunction, you could use De Morgan, convert this to all ORs, and then apply the associativity of disjunction. Any questions? I guess these are clear exercises, and it's just a matter of writing the details, applying the De Morgan, and using the same property that we know is true for disjunction. And then now we know these are true. Conjunction is both symmetric and associative. Another theorem, it's a very obvious one. Any formula and top has to be equivalent to that formula. If you want to think about this semantically, then note that top is a tautology. Any formula and a tautology, it has exact same truth value of the formula itself. I'll just say this one more time, that here we don't, at this point, we are not working with semantics, so everything is purely syntactical, but the whole point of this, those axioms and rules of inference, was that you're constructing a system of proof that coincides with our semantics. So that means if something is an absolute theorem, it's going to be a tautology, and vice versa. This is true for everything that we prove, right? So this guides you to understand why such a thing is provable, why such a formula is an absolute theorem, because it's a tautology. And later on, we'll see that why these two coincide. So now, how do we prove this? I guess probably golden rule is going to help us again. So let's write the whole thing. A and top is equivalent to A. Why golden rule is equivalent to A or top. Sorry, did I want this? I guess we haven't proved this here. Sorry, just one moment. I don't think we have proved this yet. We don't know if this is true, so we need to come up with a better plan. Let me see. What did we prove? Okay, I think we can use this theorem. A and A is A. So let's start with the whole thing. And I want to replace the second A with A and A because they're equivalent and we have proved them. So I'll annotate here, I'm using Leibniz. I call this P, and I use the absolute theorem A and A is equivalent to A, where the C part is A and top is equivalent to P. P fresh. Now we have this. Now we can use the distributivity. This is equivalent to okay, this is equivalent to A and A equivalent, or top is equivalent to A. top is equivalent to A is equivalent to A, and I get, okay, yeah, it works. So this is the distributivity of and over this. It's not an axiom, but I believe you proved this last time. Let me go back and find where it was. Or I'm pretty sure we proved it. I can't find it. Okay. Let me think for a second. This is, I mean, we do have this distributive. I just don't remember if we proved it. If we didn't, because right now it would be just easy because we know A is equivalent to top is equivalent to A, so we get A, and we just proved that it's an absolute theorem. Now the only thing is that I don't remember is that we proved this one, and if we didn't, how else would I prove this? A and top. A and top. Yeah, okay, we can, I think we proved this, but if we didn't, I'll write it later on, another proof for this. When it comes to my mind, I'll just replace it with something else, another proof, but we have the distributivity and we can use it. So this last step is another Leibniz where I replace this with A. So Leibniz, top is equivalent to A is equivalent to A. That's the redundant true. Now the C part, I replace this with A. So it's going to be A and P. And P is fresh. All right. Yes. Hold on. No, but these are not the same. The first and third part, you're saying they're the same, but this, notice that this here is this. And this here is, these are completely different formulas, right? Because and conjunction has priority over by implication. So it's not that the first and third step are the same. Yes. So we substitute, sorry, I didn't understand. Substitute top for A? Where? Instead of this, have it A and A. Let me see. Top. What? I mean, how can you replace top with A? No, I mean, A is not an absolute thing. You cannot replace, A is not equivalent to top, right? This is not a theorem. Right? You cannot replace A with top. But I'm sure there's an easier way to do this. I mean, there are a lot of other things come to my mind, but they might be more difficult. So I'm not gonna try those. If I had A and all right, yeah, let's leave it. I think all right, this is a correct proof, anyways. Another theorem is that A and bottom is equivalent to bottom, and this is just a golden rule, right? A and bottom equivalent to bottom is equivalent to A or bottom equivalent to A. It's the axiom of golden rule, all of it. This is equivalent to this. So any formula and bottom is equivalent to bottom. Another distributivity is the distributivity of disjunction over conjunction. That if you have A or B and C, it's equivalent to A or B and A or C. Now, to prove this, we're gonna use a slightly more different method. We're gonna use equational style proofs, but we're going to start with this direction and show that it's equivalent to a formula. Let's name it D. So we're going to show that it's equivalent to formula D. And then we're going to start from this side and simplify, use an equational style proof, and show that this is also equivalent to D. So they're both being equivalent to D, they would be equivalent, right, by the transitivity of by implication. So let's start from the left-hand side. No, sorry, first right-hand side. A or B, and A or C using the golden rule. We call this formula D, call this formula E. D and E is equivalent to D, or E is equivalent to D is equivalent to E, which is exactly this formula here. Now, look at this here. What do I want to do? I have here two A's, right? And I know OR is symmetric. So basically here, I have A or B or C. And A or A is same as A. So let's just eliminate that. First, let's swap these two, apply the symmetry, call this P. And the C part is the entire formula where this part is replaced with P. And using Leibniz, I can switch this with A or B, right? Then what do I get? I get A or B or C is equivalent to A or B, equivalent to A or C. Now I know A or A is equivalent to A. So let's call this P. So the C part of the Leibniz is P or B or C is equivalent to A or B, equivalent to A or C. And then I'm allowed to replace A or A with A. So we have this. Now, it's not completely clear where to go from at this stage. We're stuck with this formula. There's no obvious thing like double negation or De Morgan or golden rule to do here. So at this stage, we'll just go back and start with this side. So we just leave it there. Now let's simplify this side, and we're going to show that after some operations, well, some equivalences, this part is also equivalent to the same thing. So now let's look at the right hand side. We have A or B and C. We're going to apply golden rule to this part of the formula, because we know B and C is equivalent to B, or C equivalent to B equivalent to C. That's what golden rule says, right? Golden rule says B and C is equivalent to B, or C is equivalent to B equivalent to C. Now, if the C part of the Leibniz is A or P, I can replace P with this equivalent formula. So what do we get? A or this. B or C is equivalent to B is equivalent to C. Now, one of our axioms was the distributivity of disjunction over by implication. And here I have a disjunction, this one, and by implication, I'm going to take this one. Now call this formula D, call this formula E. A or D is equivalent to E. You can apply the distributivity here, and what you get is A or D. A or D is equivalent to A or E. Now use the distributivity again. Now this time for this side, right? I know I can distribute here or over by implication. I just need to call this P and apply Leibniz. The C part of the Leibniz is going to be A or B or C is equivalent to P, where P is a fresh variable, doesn't occur in any of the formulas that we have, A, B, or C. And now you can replace P with the other side of the distribution, which is A or B is equivalent to A or C. Now notice that this is exactly the same formula. So what we showed is that both sides of this equivalence, they're equivalent to the same formula. And then the transitivity. So you've basically shown that A is equivalent to some D, but also B is equivalent to the same D. The transitivity tells you that A is equivalent to B. That's the transitivity of by implication that we proved, I think 2 lectures ago. Any questions here? See, there are a lot of different methods to write a proof for an absolute or even a relative formula. It's just a matter of practice so that you can come up with the most efficient and easiest proof. There are really many different ways to prove this one. Probably this one is the simplest, but who knows, maybe someone can come up with something better. Now we prove distributivity of or over and, but you can also distribute and over or. A and B or C is equivalent to A and B or A and C. Now the proof of this one is exercise, but notice that you don't have to go through all these steps again, similar steps. But now you can apply, you can use this distributivity. And I guess the obvious idea would be to change this and to or and this or to and using De Morgan. So you're going to have a bunch of negations there as well. But then after applying these two De Morgans, then you can use the distributivity of or over and, which we just proved. So once we prove something, we can use it, and you see that how they are helping us to prove more things. So every time we prove something, the next proof is going to become easier. And here's a remark that again, by the symmetry of the conjunction, also symmetry of disjunction, and also symmetry of conjunction, we can distribute or over and or and over or from any direction, from right or left. And the proofs are, again, just one using just one symmetry, that we can distribute and over or from the right side. So we have this, and you can distribute or over and also from right side. So we have this absolute theorem. Again, the proofs are, I leave them as exercise. You can just, again, there's nothing there. It's just symmetry. Use one Leibniz, apply symmetry, and you are done. Now, another theorem. Let's see. This one says A or B implies C is equivalent to A implies C and B implies C. This is actually a very important identity that what we use a lot in mathematics is called proof by cases. That if you have A or B implies C, you want to show that if you have two cases, if your hypothesis consists of two separate cases, A or B, it's like, for example, an integer is either even or odd, then you prove something. Then you can first prove it for even cases and then prove C for odd cases. So this is what we call in mathematics proof by cases, and it comes from this absolute theorem or this tautology that A or B implies C is equivalent to A implies C and B implies C. But let's prove this. Let's start with this side. This is equivalent to negation. Whenever you see a formula implies another formula, the best identity, the most useful identity, when I say identity, I mean equivalence, is this equivalence. So this would give me negation of A and B or C. What did we use? We used the fact that A implies B is equivalent to negation of A or B. This is the theorem that we used. Now, obviously, we want to apply De Morgan here. Okay, if I wanted to be picky, I would have to write, because the way that we stated De Morgan was this, right? The negation of, no, A or B is equivalent to negation of A and negation of B. So let's be picky and write it the way it is. So I'm going to call this P and replace it with this. The difference is that now we're going to get double negation, right? But we want to be precise. This end. So what did we do? We applied Leibniz to the Morgan or the Morgan law. There's the C part is the formula negation of P or C, where P is fresh. And then we got this. And now it's obvious that we want to apply double negation to get rid of these two. So what is the C part of the Leibniz? This entire thing, I want to call it P and replace it with negation of A and negation of B. And that would give me negation of A and negation of B or C. What did we do? We used Leibniz, double negation. What was the C part? It was P or C, where P is fresh. And now what? We can distribute or over N. What do we get? We get negation of A or C and negation of B or C. What did we do? We applied the distributivity of disjunction over conjunction. Now I think it's clear what we have. I'm going to call this P. And you know P is equivalent to A implies C. Use Leibniz. So Leibniz A implies B is equivalent to negation of A or B. That's the equivalence that we are using. What's the C part? C part is P and negation of B or C, P fresh. Gonna have one more step of the same type. So, oops. The last step is to replace negation of B or C with B implies C by calling this P and replacing it using a Leibniz. Leibniz, the same absolute theorem. The C part is A implies C and P. And P is fresh. Any questions here? I think I said before that you shouldn't worry about what we have proved so far and what we haven't, what we're allowed to use. In the exam, midterm or final exam, I'll give you the list of all the axioms and all the theorems that we proved in the class, and you're allowed to use all of them, right? So you don't have to memorize them, and I mean, there's always, I mean, I would forget which one we have proved, which one we haven't proved. So I don't expect you to remember that. So don't worry about it. I'll give you the list. Another theorem, A implies B and C is equivalent to A implies B and A implies C. Another important tautology or an absolute theorem that it has a lot of applications. Let's start with the left-hand side. Note that I didn't write the brackets here, but because conjunction has priority over implication, it's the same thing. It's A implies B and C. Now, using the absolute theorem, we can replace this implication with negation of A or B and C. Right? So these are equivalent. Now distribute this disjunction over conjunction. You get negation of B, negation of A or B, and negation of A or C. Now, here, sometimes we get lazy and do two Leibniz that are similar in one step. I didn't even say what this C parts are, but I think this is clear that first step you use the Leibniz, you call this P, and you replace this P with A implies B. And after that, you use the Leibniz again, and now you call this one P, and you replace this P with A implies C. So Leibniz twice for this formula will give you what we want. And even in the exam, if there are, or even in the assignments, if there are these kind of obvious Leibniz, there are multiple Leibniz in a row, and they're obvious, you can do the same thing. Just say Leibniz twice or three times, if you will. You wouldn't lose any points. Another theorem. This theorem, I'm not going to prove it. Actually, I wrote a sketch of the proof because it's a little bit long and maybe not obvious. But what is the theorem? Is that A is equivalent to B is equivalent to A implies B and B implies A, which is a very, very important identity that describes what the by implication is and how it reacts to implication. Obviously, by implication means if and only if. A is equivalent to B is same as A implies B and B implies A, which is exactly what this theorem says. So this is something that we expect to be true, otherwise our system of proof is completely nonsense. But it is true, but the proof is, as I said, it's not completely obvious. So I only written the sketch of the proof from your textbook. You could, if you wanted to see them, to see more details, then you can look it up in your textbook. So yeah, here A implies B. Well, here why it's tricky, but because instead of replacing this with the negation of A or B, we have replaced it with, we have used the axiom of introduction of implication. You have replaced A implies B with A or B is equivalent to B, and you do the same thing here. I don't know it's actually what happens if I replace it with A negation of A or B, and then we get here negation of B or A or A. Okay, you see the problem here. If you did this, then it's not obvious what we do here. You could distribute this, you could call this formula D and distribute it over this. Then you distribute again. Okay, maybe it is possible to do it in a different way, but I guess I don't have time to do it in the class. You could try it. Maybe you'll get stuck, maybe you won't. Maybe you'll have an easier proof. I don't know, but yeah, there are different methods to prove things. But in any case, this is not going to be a short proof. This is going to be a long proof. And here's one way to do it, right? You use that, and then you apply the axiom of golden rule. When you call this formula D, let's call this formula E, then D and E is equivalent to D, or E is equivalent to D is equivalent to E. You write all that, then this is what you get. And then you apply the redundant true for this part, because you have, let me see, yes, you have a formula, let's call it D again. D is equivalent to D is equivalent to top. So I mean, this step is obvious. A or B equivalent to A or B, we just replace at the top using proper Leibniz. So this is what you get in the next step. Now what? Now you have again some obvious things, and that is, no, yeah, A equivalent to B equivalent to top. Any formula equivalent to top is equivalent to the formula. So this is equivalent to A equivalent to B. And then you apply Leibniz with another theorem. Which theorem that is? I think you just distribute everything inside. Yeah, you just distribute this entire formula. Take it first, this formula D, distribute it over these two, and then you distribute one more time from this one. Anyways, it's a long one, so that's why I didn't want to do it, right? You end up with this, and few more axioms and so on. It continues. Finally, you get A is equivalent to B, and done. So you can read the proof, but or you can, if you just wanted to practice steps. Otherwise, I'm not expecting you to know this or be able to write such a long and complicated one. All right. So far, all the equation style proofs that we wrote were for absolute theorem, and at this point it's not clear how to use assumptions or hypotheses in an equational style proof, right? In the Hilbert style proof, it was completely easy, right? You at any step you may write the hypothesis, and you just say hypothesis. But where do we use hypothesis? So I want to show that gamma proves A by using equational style proof rather than the Hilbert style. Where do I use the hypothesis from gamma? Since, okay, if I start from A and if I wanted to show that it's equivalent to an absolute theorem, at some point I would need to use formulas or hypotheses that are in gamma. The identity or the equivalence that allows us to do that is the redundant true, because redundant true tells us that A is equivalent to A is equivalent to top. Right? This is what we call redundant true. And now, I think I proved this before, that if a gamma proves A, we did it for tautological implication. We didn't prove it. But okay, let me remind you that for tautological implication, we had this. No, I think we even proved it. Yes, we proved this even for. So this theorem that I've written here, we proved it, I think last time or 2 lectures ago, that if, as a consequence of this redundant true, we have that if gamma proves A, then gamma proves A is equivalent to A, right? You just apply the redundant true and equanimity. And vice versa. If gamma proves A is equivalent to top, then gamma proves A. Now, what does that tell us? Suppose now if I had a formula A, which is in gamma. So that means it's a hypothesis. Then obviously gamma can prove A. There's a one-step Hilbert style proof for this. At the first step, write A. Now by this theorem, or this method theorem, gamma proves A is equivalent to top. So what does this tell us? It tells us that if A is a hypothesis, then A equivalent to top is a relative theorem. It's a gamma theorem in this case. So that means I can replace any hypothesis with top, right? So this means if A belongs to gamma in any proof, we can replace A with top. Possibly using a Leibniz, right? So for example here, let's show that A and B can prove A and B. Let's start with the formula A and B. Now, I know B is a hypothesis. And from what we said, from the consequence of redundant true, I can replace B with top. Why? Because B is a hypothesis. So in the annotation, so I'm going to call this P. I know B is equivalent to top. So my gamma implies B is equivalent to top. I don't even need A. B proves B is equivalent to top. But by strengthening hypothesis, A and B also proves B is equivalent to top. So we can take this as a theorem. Everywhere we can replace B with top. Here I have B. I call this P. Use Leibniz because B is a hypothesis, or you could write because B is equivalent to top. This is a hypothesis. The C part is going to be A or A and P. Now you can replace B with top. You get A and top. A and top, today we proved it's equivalent to A. Now, why are we done? Because A and B is equivalent to A, but A is the other hypothesis, in which we know it's true, because our hypothesis is equivalent to top. So this formula is equivalent to top, right? If I wanted to continue with this, I know that, I mean, we don't have to. This is equivalent to top. Even I know A is equivalent to top, so there's even no need for that. A is equivalent to top. Therefore, this formula is equivalent to top. Any formula equivalent to top is an absolute theorem. That's, again, redundant true. If you have a formula that's equivalent to top, redundant true tells you that this is also equivalent to A is equivalent to top. Now you apply equanimity, get A. Sorry. Any questions? Another one, A or A proves A. I mean, this is very easy because we know we have an axiom A is equivalent to A or A. So for the formula that we wanted to prove is equivalent to our hypothesis. Since we assume hypothesis is true, A is true. Another one, A proves A or B for any formula B. Let's start with A or B. We know A is a hypothesis, so it's equivalent to top. Now, how do we go from here? We just call this P. Use Leibniz. Since A is a hypothesis, it's equivalent to top. Replace A with top. What do we get? We get top or B. Any formula or B is an absolute theorem. Again, this was proved somewhere today. Yeah, we proved it today. I'm not going back. Any formula over top is an absolute theorem. So these are very easy. I'll just go quickly. A and B proves A. All right, let me think about this. What do we have proved here? A and B. We have proved this. Let's think about this for a second and see how we can prove this. A and B is a hypothesis, so it's equivalent to top. Now, we want to get A. I want to, start with A. I want to create A and B. How do I create A and B? Maybe I write this as A is equivalent. Before I write a complete proof, let me make a strategy. I know A is equivalent to top. Now, instead of top, I can write B. So I'll get A is equivalent to B. No, I don't have B. Sorry, I have A and B. B is not a hypothesis. How about we use all right, sorry, let me think about this. A is same as A. Okay. Yeah, I see. A is same as A or bottom, right? So A is same as A or bottom, and also is same as A and top. This is better. Now A and top, I can replace it with A and B here. Now I get here A and A and B, but A and B is just same as A. So we are done. We get A and B. All right, so it works. So now let's write the proof. I started with A, and I know A is equivalent to A and top. I'll write just absolute theorem. Now using Leibniz, since hypothesis is A and B, that means A and B is equivalent to top. So C part is A and P. I call this P. I want to replace it with my hypothesis. Refresh. Oops, I forgot to write A and B. A and B. Note that well, technically I have this, but by associativity, I have this because today we saw that conjunction is associative. So I have A and B. And today we also saw that A and A is equivalent to A. Where did we see it? Somewhere. Sorry, I'm gonna go find it because this is, I think we proved that, didn't we? Yeah, here. A and A is equivalent to A. So I'm using this theorem. It's hard to remember which one I've proved, which one I haven't, but All right, A and A is equivalent to A is an absolute theorem. Now, what do we get? We need to use Leibniz, sorry. Leibniz, we call this P A and A is equivalent to A. The C part of the Leibniz is P and B, where P is fresh. What do I get? A and B. Now, A and B is equivalent to A conjunction with B. Sorry, A is equivalent to A conjunction with B. Note that this is not in general true, but if you give me the hypothesis A and B, then it's true. Now we are done because A and B is a hypothesis. So A is equivalent to our hypothesis. That means it's true. All right, I'll stop here. Are there any questions? All right, if not, have a nice day, everyone. And I'll see you next week.